Alright, now we'll continue our problem, our sample problem for the buoyancy topic. Now for the problem number 2, a cube 0.5 on its side is made of bronze and the unit weight is 86.9 kilonewton per meter cube. Determine the magnitude and the direction of the force required to hold the cube in equilibrium when completely submerged in the water. Okay, so our condition is a fully submerged, and um, the sides, I mean, the length is given plus the unit weight. So therefore, we can solve for the weight force, the downward force, and then once we've solved for that, then we can apply the equilibrium equations, and then we can find the unknowns. Okay, so for the solution, I guess we'll first start with solve for the weight. Right? Solve for the weight of the cube. Okay, so the weight is just simply W times the unit weight times the volume of the cube. And the unit weight is 86.9. That's in kilonewton per meter cube times the volume. Okay, so we have this volume 0.5 by 0.5. Okay, so since it's a cube, then it's just the same as the other problem we had, 0.5 raised to 3. Okay, and when you do the math, what you will get is 10.86 kilonewtons. Okay, so we have the weight, and I guess we can also find the buoyant force. Why? It's because we have this displaced volume. The volume of the solid is just equal to the displaced volume because it is fully submerged. Okay, so solve for the buoyant force. Okay, so F sub B is equal to the weight of the fluid times the displaced volume. Okay, so the unit weight of the fluid in terms of kilonewtons per meter cube, that's 9.81 kilonewton per meter cube times the volume, which is 0.5 meters raised to 3. Okay, and if you do the math, what you get is 1.23 kilonewtons. Okay, so we have the weight, we have the buoyant force. Now uh, it shows here that the weight is greater than the buoyant force, and therefore our expectation is that it will actually sink or it will move downward. Okay, but the problem says that we are to determine the magnitude and direction of the force required to hold the cube in equilibrium when completely submerged. So there must be some force acting upward, or let's say a rope or a chain, for example, wherein this submerged body is being hung or is in equilibrium. Okay, so there must be some force right here because it says here that determine the magnitude and direction of the force required to hold the cube in equilibrium. So since they're all, I mean, since it's going downward, the tendency of this situation is that this block will go downward, then the force has to go upward. Okay, so that it will not go anywhere. Okay, so for the third step, applying now the equilibrium equation. Of course, if we have to apply that, we have to draw our equilibrium, I mean our free body diagram. And let's say this is our weight, then this is our free body. I mean, this is our uh, buoyant force, and of course, you'll still have force right here. And by the way, this buoyant force should be also acting along the centroid, except that I just draw it somewhat offset simply to show that there's a buoyant force right here. Okay, so summation of forces y is equal to 0, and let's assume that the upward direction is positive. Then therefore, by the way, we'll label this as the let's say our P, right? Force P required to hold this body or this submerged body in equilibrium. Okay, so P plus F sub P, right, minus the downward direction of the weight is equal to 0. Therefore, P is just simply weight minus the free minus the buoyant force. So the weight is 10.86 kN, and then the buoyant force is 1.23 kN. Therefore, our force, maintaining force, is 9.63 kN. All right. Now we'll do another problem. Okay, so problem number 3, it says here a uniform block of steel with an SG of 7.85 will float at a mercury water interface as in the figure. What is the ratio of the distances A and B for this condition? Okay, so the situation is that we have two layers of fluid. We have the water, and then we have the mercury, the Hg. And then our block, or our steel block, is actually submerged, or I mean totally submerged in these two fluids, but except that half half of the volume, or some portion of the volume is submerged in water, while the other remaining portion is submerged in the mercury fluid. And we have this distance A and B. And the problem says we are to find the this ratio of A over B. Okay, so for the solution, since we have an unknown right here, A, B, and then we don't also know the buoyant force and the weight, and I guess we can, the first step is to set up the equations. So let's try to obtain equations. Obtain equation from free body diagram. Okay, so this is our block, and we have this distance. We have the distance right here. That's distance A and distance B. And therefore, our forces would be the force, the weight of the block. That's weight. And we'll also have the buoyant force, F sub B, from the mercury. That's right here, Hg, and then this one is water. Okay, so Fb, right, that's the buoyant force induced by this mercury fluid layer, right? And another buoyant force, that's right here, F sub B, from the water. And therefore, if we apply the equilibrium equation, summation of forces y is equal to 0, and we can see that the weight is just equal to the buoyant force induced by the mercury plus the buoyant force induced by the water. Okay, and let's label this equation number 1. Okay, the next one is, let's try to solve for the weight. let's try to solve for the value of the weight and then the value of this um, of this buoyant force from the mercury, and then also the buoyant force from the water. So solving the weight of the block. So W is just equal to the unit weight times the volume. Okay, the unit weight is Sg times the unit weight of water. So that's 7.85 Sg times 9.81 kilonewton per meter cube. Okay, now the volume is um, we're not actually given the dimension of this block, but then we can just write the equation of the volume is just area times the depth, right? And that depth is basically this depth. Right? So this is A plus B. So this is A, this is B, then therefore the total length would just be A plus B. Therefore we can just write A, the volume is area times A plus B. Okay, now let's try to express the weight per area. Okay, weight per area, since we will have the same area, whether it's in water or in mercury, we'll have the same area. Then what if we'll try to express the weight in terms, weight per unit area. Okay, so weight per unit area is just this one. Okay, so the product is 77. That's 77 kilonewton per meter cube. And then the remaining terms here is just the A plus B. Now let's say this is our equation number 2. Okay, now the third step is let's try to solve for the unit weight of the mercury or the water. Solving for FB. Okay, let's try the water first. FB water. Okay, so FB water is equal to simply the unit weight, right? That's the unit weight of the water times the displaced volume, but of course referring to the displaced volume at the fluid, at the water surface. Okay, so what is the unit weight of water? It's just 9.81 kN per meter cube. And then the volume, it just refers to this volume, the area, okay, the area, this length times the orthogonal length that's projecting or perpendicular from this paper or from this plane. Okay, and then times the height, which is A. Okay, so the area times the height. Okay, and therefore we can also express this buoyant force per unit area is just equal to 9.81 kilonewton per meter cube times the depth. Now let's say this is our equation number 3. Okay, so for the fourth step, solve for the buoyant force induced by the mercury. Okay, so FBHG is just equal to the unit weight of mercury times the volume displaced in the mercury layer. Okay, so the unit weight of mercury is just 13.6 times 9.81. That's in kilonewton per meter cube. Okay, this one is the specific gravity times 9.81. That's the unit weight. Times the volume displaced in the mercury layer. And that volume displaced is just again equal to the area So the area, okay, if you try to draw a three-dimensional here, that refers to this area right here. Okay, so the area times the depth, that will give us the volume. Okay, so area times the depth, but the depth is B, right? A times B. And therefore, we can also express the buoyant force from, buoyant force provided by the Mercury per unit area, and that's equal to 133.42 kilonewton per meter cube times B. Okay, and that's our equation number 4. Now, step number 5, substitute equation number, okay, the weight, this one, equation 2, equation 3, and equation 4. Let's substitute this to equation number 1. Okay, so substitute equation 2, 3, and 4 to equation 1. Okay, so the weight, okay, that's the weight. So that's actually weight per unit area. Okay, so weight per unit area is equal to this one, FB Hg per unit area plus FB, the buoyant force induced by the water per unit area. And since we have all the area in the denominator, then it just cancels out. Okay, so the weight is 77, right? 77 A plus B is equal to the buoyant force by the Mercury, which is 133.42. That's B, right? And then plus this one, 9.81 times A, 9.81 times A. Okay, so in this equation, we have the unknowns left are A and B. Okay, so two equations, two unknowns. Supposedly, we need two equations. However, the problem only asked us to solve for the ratio. Okay, so that means we need to solve for the A over B. Okay, so if we expound the terms, we have 77A plus 77B is equal to 133.42B plus 9.81 A. Okay, so let's try to group the A on one side, or on the left side, 77A minus, right, this term, minus 9.81A is equal to 133.42B minus this term, 77B. Okay, and what we get is 67.19A is equal to 56.42B. Therefore, if we want to find the A over B, that's the ratio. That's going to be 56.42 divided by 67.19. Okay, note that they have the same units, and therefore the units just cancels out. So we don't have a unit for the ratio, and the value is 0.84. Right, so this is our answer. Okay, so again, if we review our solution process, then we have this problem. Um, it's a two-layer fluid, and we are asked to find for the ratio of this distances. So the first thing that we did is to obtain the relationship, or is to apply the equilibrium equations and draw the free body diagram, so that we can find the unknowns, or which one can be solved directly or later on. Okay, so when we apply this equilibrium conditions, we found that the weight is just simply equal to the force, the buoyant force provided by the mercury plus the buoyant force provided by the water. Okay, so after this, we solve individually the values or the magnitude of the weight. And so the weight is just simply the unit weight times the volume, and then we just substitute the values, and except that our unknown here is the depth. Okay, so that's A plus B. So we use the weight per unit area because the area is just actually um, the same, the same with the same in the weight term, the same in the buoyant force term. So we just express this weight in terms of per unit area. Okay, so this is our equation 2. Then the next step that we did is to solve for the buoyant force of the water. So we just apply this equation, and we only consider the volume displaced by the water, which is area times the depth A. Okay, and then we arrive in this expression. Then the last, um, not the last step, the next step that we did is to solve the buoyant force provided by the mercury. Okay, so again, it's just unit weight times the displaced volume, except that this displaced volume corresponds to the depth of the uh, depth within this mercury layer. Okay, so we apply that, and then we obtain this equation, and that's equation number 4. And the last step that we did is to substitute all the values of the weight, the buoyant forces in our equation number 1. Okay, so since we have two unknowns right here, A and B, um, we, we should need two equations to solve for the value of A or the value of B. However, the problem only asks us to find for the ratio only. So that's going to be A over B, which is the ratio. We apply we substitute all the values and then do the math, and we obtain a value of 0.84. All right, I guess that's enough for our topic on buoyancy, but I'd also like to discuss it here, even just briefly, regarding the concept of stability. Okay, so in the textbooks, you will notice that the chapter on buoyancy, it's actually integrated, or they go hand in hand with buoyancy and stability. Okay, so for the concept of stability, a body in a fluid is considered stable if it will return to its original position after being rotated a small amount, a small amount about the horizontal axis. Okay, so for example, this is our body, and we have this surface, this free surface, for example, and then this is our axis of rotation, for example. Then we try um, to um, to tilt this body, for example. I think it will be best shown if we're looking at, okay, let's say this is our xy and then this is our z. So if we look at the xy plane, this is our z. Then if this is our body and this is our free surface, then this is our um, axis of rotation. So if we rotate it in this position, if we rotate this body in this position, if it returns back to the original position, then um, it is said that that the condition is stable, or the body is stable. Now the question is, why do we worry about this? Why do we worry about stability? Okay, so the the reason for that is, if we want to design, for example, ships or air balloons, yes, I think ships and air balloons. So no matter how the external forces acts at the ship, it would be necessary if it can be stable, or not be affected by those forces. Okay, so it's really an important concept. Okay, so the concept of stability, it actually applies, although it applies to both submerged and floating bodies, but it's more, I think it's more related to the floating bodies. Okay, so again, the concept of stability both applies to submerged bodies, except that most of the applications probably is with regard to the floating bodies. Okay, so in these floating bodies, we have three types of stability. So the first one, we have a stable condition. The second one is unstable condition, and the third one is the neutral equilibrium. Okay, so the concept here is that if this is our free surface and we have our body right here, and in this body we have, of course, a center of gravity, a center of gravity, right? So this is our C sub g. So the C sub g will induce weight, right? Now, let's say this is our displaced volume. Okay, so this displaced volume, it has also a centroid, right? And let's say this is our centroid. Now, for this centroid, that's where our the centroid is the center of buoyancy. That's where the buoyant force is acting. If we say that we have a heavier bottom right here, so let's say it's not a uniform mass object, so it is heavier at the bottom. Okay, so if that's going to be the case, then if CG is, okay, so if CG is above, right, is above F sub B, then that's going to be the case for unstable condition. By the way, I think this heavy this heavy portion should be at the top portion. Okay, so if it's more heavy on top, then of course it's not going to be stable. Okay, so again, the heavier portion would be on this top portion. So if you can imagine that if you have a heavier top, of course, that's not going to be stable. Okay, so that's why this is the unstable condition. Okay, so what if you'll have a heavier bottom? Now, if our bottom is heavy, then of course the center of gravity would be close to this concentrated mass or something. Okay, and that's our CG. Okay, and then of course, since this is the displaced volume, then somewhere right here, let's say this is our center of buoyancy, C sub B. Now, if our CG is below the C sub B, right? This one should be C sub B. Then we have a stable condition. Then for the neutral equilibrium, um, it's just, let's say it's fully submerged and then they both act. I mean, the buoyant force plus the weight, or let's say the CB and the CG, they actually coincide with each other in this view, or in this side view. Then that's what we call as neutral equilibrium. All right, so I guess we'll just stop with I mean, we'll just stop here, and then in the next video we'll be moving on to our next topic. So we're not gonna solve much about this concept. There's also a lot of computations regarding here, and a lot of new terms that's involved, but I guess that would be enough for us given the time. That's enough for us to just introduce this concept. All right, so see you in the next video.